Now we understand bias-variance trade-off. Let's examine different methods of doing regularization, lasso and ridge regression. So we have seen this example where the simple model is not varying a lot, where the complex model is varying a lot. Variance is low on the simple model and the variance is high on the complex model. One thing we should examine also is the values of the coefficients for the simple model and the complex model. What we see is that for the simple model, the coefficients vary little, where in the complex model, the values of the coefficients vary a lot, and they get enormous, extreme values. Now, model selection is the application of the principal method to determine the complexity of the model. For example, choosing a subset of predictors or choosing the degree of the polynomial model, etc. A strong motivation for performing model selection is to avoid overfitting, which we saw can happen when the feature space has high dimensionality or too many predictors, the polynomial degree is too high, or we consider too many cross terms. Now we see a different way of doing model selection. The coefficient values are too extreme. Now, how do we discourage extreme values in the model parameters? So what we want is low model error, as before, and now we want to discourage extreme parameter values. How do we do that? Well, for the low model error, we know we want to minimize the MSE. How do we discourage a model from having extreme parameters? Well, there's a couple of ways of doing it. The first one is we sum the square of the values of the parameters, or we sum the absolute value of the parameters. So how do we combine these two conditions? Well, we can add them up, or we can add them up and also multiply the extra term by some parameter which we're going to call regularization parameter, and we use the Greek letter lambda for it. Now, this lambda controls the relative importance between the model error and the regularization term. A regularization term is what controls the extreme parameters. Now, if lambda is 0, we don't worry about the extreme parameter values, and therefore we back to the simple linear regression. If lambda is very large, the only thing we care is about the values of the parameters, and the model will yield betas is equal to 0. The coefficients will all turn to 0. Somewhere between lambda is equal to 0 and lambda is very large is where we want to be. So how do we determine lambda? As usually, we do validation or cross-validation. A couple of things to note is that the sum of the absolute values of the beta is the L1 norm of the vector beta. Also note that we don't include the bias in our regularization term. Why is that? Because beta is not connected to the predictors, so it doesn't contribute to the overfitting. Now, lasso regression means minimizing the lasso loss function with respect to betas, and the lasso loss function is the addition of MSE and the regularization term, which is the sum of the absolute values of the betas. Ridge regression means minimizing the ridge loss with respect to betas, and the ridge loss is the sum of the MSE plus the sum of the square of the betas. Again, note that the sum of the square of the betas is also known as the square of L2 norm of the vector beta. And again, you may hear the term L2 regularization. Also note, even in the ridge regression, we don't include the bias for the same reason as before, because it's not connected to the predictors. How do we choose the regularization parameter with just validation set only? We select lambda from a very small value to the very large value, and for each value of lambda, we record the MSE for the validation set, and then eventually we select the lambda that gives us the lowest loss value for the validation set. We can do the same with cross-validation. And now for every fold, we do the same thing, meaning we record the loss for the validation set for every fold. Eventually, we take the average of all these values, and we select the lambda that minimizes the average loss on the validation set.